Okay, we're going to go over some video solutions to practice test number 3. Okay, looks like problem 1, we have a CDF formula given, and we want to compute some a probability and an inverse probability. So let's go to y equals, put that in. If we have a CDF, I like to put CDFs in y4. So we're going to put that in here, 1 divided by, well, you have to be very careful of your parentheses when you're putting these in. Remember to put the numerator and denominator in parentheses. Since the numerator is a single number, we can get by without that. 1 plus 6 e to the power parentheses negative 0 point 0 here is optional, but I'm going to do it 0.09 x close parentheses for the power, close parentheses for the denominator. Now I have the newer operating system with that version of it there. So we're going to graph this. CDFs always you can go a y value basically from 0 to 1. But I'm going to go a little below that, negative 0.2, and we're going to go up to 1.1, going up by 0.1. Now, this one it doesn't say, so I guess we can assume that it's all real numbers for this. So let's try negative 10 to 10, and let's see if that looks right. Now what we should see, if it's done right, it should start at 0 and then end up at 1. Okay, we're not nearly far enough to the right to be close to 1 yet. We're pretty close to 0 on the left. So let's go a little further to the left, negative 20, but let's go quite a bit further to the right. How about, let's start with 60. If we're going to do that, let's mark it off in maybe 5s or 10s. Let's see how this goes. Okay, that's closer to 0 on the left, and it's starting to level out pretty close to 1. This is not bad. I'm going to go just a little bit further to the right. Let's go ahead and go on out to 80. And we should see it leveling off pretty much at 1. Okay, that's a pretty good view, and that's what we would expect a CDF to look like. So we want the probability that x is less than 5. That is the CDF of 5. So from here I can do it a couple ways. I can hit trace and just type in 5 and enter, and that gives me the value. 4 decimal places, that's 0.2072. 272. Okay. Okay. Another way we can do the same thing from the home screen here is we can let's see, where did I have that? I had that in y4. So we can just do y4 of 5. I can do alpha F4 up here, alpha trace, to get y4. And we can say that is of 5. And that's the same number. Now, the probability that x is between 2 and 5 is the probability that x is less than 5 minus the probability that x is less than 2. And so we can find that actually from the home screen by doing y4, let's see, alpha here, and do y4 of 5 minus y4 of 2. Now if you don't have the newer operating system, you have to go to variables, right arrow to y variables, choose function, and then choose wherever your CDF is, which is in my case in 4, y4, and then of 2. And this will give us the answer that we need here. To 4 decimal places, that's 0.04087. y4 of 5, that's y4 of 2. Let's look one more time about how that's entered in. I'm going to double check all of my work here. 1 divided by parentheses 1 plus 6 e to that power. I believe that is in there the correct way. Now if we want to find the 29th percentile, this time we're taking this graph and we know the y and we want to find x. Notice the a part, we knew the x and we wanted to find y on the CDF function. Well, if you know y and you want to find x, you graph y equals 29, and what we want to do is calculate the intersection of these two graphs, number 5. So it's going to graph the CDF and then graph I'm sorry, not 29 of course, 0.29. There we go. Oops. Okay, up here that is 0.29, and down here I messed up my formula. It should be 1 divided by parentheses, and then the rest is okay. Okay, I think this is going to work. Calculate the intersection. Now it should graph the horizontal line for us, graph the CDF, and we want to find where the two cross, and we want the x value of that. Only have two curves, so this part's easy. First curve enter, second curve enter, and I can put my guess over here. I'm going to guess, looks like around 10, and I'm going to guess that and see where we come up with. 10 was a pretty good guess. 9.9597. And so that's the 29th percentile. Next question. So now we have a triangular distribution from 9 to 18. Okay, so I'm just going to use some scratch paper here. So we're going to go from 9 to 18, and it's 0 up to 9, it's 0 past 18, so this is the x-axis right along here. And the mode is at 18, so it's going straight up like that. So that makes our little right triangle right there. Some height 8, so let's figure out the height. This is 18 minus 9 is 9 wide, and so we know the area is 1/2 base times height. So this is 9h, half of that. So this is 9/2 h is the area, but the area is 1, so the height is 2/9. Okay, that's the overall height. Okay, let's go back. Let's go ahead and see what they want us to find. We need to find a mean, median, variance, and a probability there. I'm going to go ahead and figure out a formula for this, and so we can do a little graphing. Okay, so we need to find it's y equals m x minus x sub 0. We know x sub 0 is where it crosses the axis for that line, so that's 9. And we need to find the slope. So the slope is delta y over delta x. That's the change in the y. So how far did it? So we'll notice we're from this point here to this point. We know that we're going to the right and up. So delta y is positive 2/9, and delta x is 9. So this is 2 over 81 is the slope. I'm going to go ahead and get this graph in the calculator. So I'm going to go back over here. This is a PDF, and PDFs, let me clear that and clear that from the first problem. PDFs I like to put in Y7. So I'm going to put that here and put 2 over 81, I'll put that in parentheses, times parentheses x minus 9. And this one makes sense from 9 to 18, so I'm going to graph this from 9 to 18 on the x's. Maybe we'll mark off every one this time. And later on I'm actually going to have to graph the CDF for this one, so I'm going to just leave this alone and see if this looks reasonable for a graph. Should get a triangle. We can check to see that we did some of our calculations right, because this total area should be 1. 2/9 times 9 is the 9's cancel, gives you 2, and then half of that is 1, so that's an area of 1. We can check it here on the calculator by doing calculate number 7, our area calculator, and we want to go from 9 to 18, and this should come out to be 1. Just double check. Okay, that's good news, and we can clear our drawing. Okay, now we're ready to go to compute some probabilities. We can do these by hand, or we can do it with the calculator. 14 to 17. So going back here from 14 to 17. 17's over here somewhere. 14 in here somewhere. And we're looking at an area like this. Okay, so the easiest way to do this is just with the calculator, since we've got the formula in. So I can just do a calculate number 7 for our area calculator, go from 14 to 17, and it shades it, and it gives us our area. We can also compute it from the home screen like this. We can go Math 9. This is our area calculator again. The lower is 14, the upper is 17. The formula is in Y7. And then the last part's always a dx. There's always an x there. That just basically tells us that's our variable. And so now if you have the older operating system, this would be function integrate, and the first one is the Y7. Then always the x for second one, then the lower, then the upper. So you do it that way. And it gives us the same number that we just came up with, 0.48, well, 15 approximately. We could also calculate that by hand. Now how about the mean of the distribution? The mean of the distribution in general, of course, is denoted by mu. That's also known as the expected value of x. And that is, you take x times the PDF of x, and you add that up over all x's that make sense, dx. Okay, so in our case, that's going to go from 9 to 18. We have x times, and then the PDF is in Y7 dx. So we just enter it like that in our calculator at the home screen. So that's Math 9, going from 9 to 18, x times Y7 dx. I really recommend the newer operating system if you can get it. You can download it, or I can help you with it. So this is 15. In the older system, the newer one's better, but the older one you could write FNINT. It's the same thing, just a different notation. It's times Y7, comma, x, comma, 9, comma, 18. Would be the way it looks. Still give you the same thing. Now that's 15, so let's remember that. We're going to need that in a minute. So that's 15. So now let's go to the variance next. So the variance we find is sigma square is the variance, which is the expected value of x minus mu square. So that is x minus mu square times the PDF of x, and add that up for all x's. So in our case, again, that goes from 9 to 18. Mu was, we just computed 15. PDF is in Y7. And so we just enter it that way. So I can actually I can go second entry, and this will pull up some of this. And the only thing I have to do is change the x a bit by replacing it by parentheses, and let's go to insert an x minus the 15, close parentheses, square. And that's what we need. That's going to be the variance. And that is 4.5. Of course, the standard deviation, if we needed it, would be just the square root of that answer. There we go. But I think this one asks for variance, not standard deviation. Yeah, it did ask for variance. 4.5. Now, median is an inverse probability. So to do that, we have to have a CDF. Well, we don't have a CDF, but we do have a PDF. Notice I put my formula in Y7, and I already have Y6 set up to be the PDF. I just have to do one thing to it. And so notice this is our area calculator. It calculates an area between some lower bound, L, and an arbitrary X of our PDF. So the PDF has to be in Y7. L needs to be the lowest value, or a value there, so that there's nothing below it, but the formula applies between L and X. And so notice that this applies, it's going to be 9 in this case. So we need to replace that L with a 9, or I can take 9 and store it as L. Or actually go into the formula and right here where it has the L, put 9. So if I turn that one on, that should give me the CDF, and I want the CDF to be 1/2. So I'm going to also graph, I need the Y value to be 0.5, so I'm also going to graph a Y value of 0.5. And I don't really need the Y7 turned on at this point. So there's our 0.5, and we should see a CDF. It should start at 0 and end at 1. And if you remember, I already had the Y window set up, so this should look pretty good. And the CDF is slowly graphing a little thicker, and we're going to calculate the intersection of these two graphs here in just a second, and then we'll be done with this question. So remember, when you're finding an inverse probability where we know the probability, we are graphing a horizontal line and seeing where it crosses this CDF. So this particular one is why we have to find a CDF. We could use the CDF to also find part A. It'd be, well, this time Y6 of 17 minus Y6 of 14. In fact, we'll do that here in just a second just to check, but we don't have to do that. Calculate the intersection. Since I turned off the other one, I only have 2 curves. If I left all of them here, I'd use my left or right arrow, my up or down arrows to switch between curves or among the curves that are there, and then just use my right or left arrows to move along a curve to locate my guess there. And so this X value is what we're looking for. The Y value, of course, is 0.5, which is the cumulative probability. Y values on the CDF are cumulative probabilities. So this one is 15.3640 when that rounds off. So the next question. Alright, so now we just have some concept questions here. Answer the following questions, comparing and contrasting the CDF of discrete and continuous distributions. Scroll down to see all the questions. Choose the single best response for each question. Let me see if I can okay, I can make some of the text not bigger, but not the part that matters. Okay. Alright, so let's just keep reading here. So notice this, these should be about the cumulative density function. There may be a similar question about the PDF. Alright, see what we got here. The graph of the cumulative density function, CDF, is always 0 or approaches 0 on the extreme left of the graph for a discrete distribution. That's true for both discrete and continuous distributions. So that's the answer. Number 2 is also true because it says the same thing about a continuous distribution. Those are both true. The graph of the CDF is always 1 or approaches 1 on the extreme right of the graph for a discrete. True. and also true for continuous. So remember, this is a cumulative probability. So there is either some point for which to the left of it it's 0, or as you go out towards negative infinity, way out to the left, it approaches 0. But then as you go to the right, you pick up more and more probability density, and so you're accumulating more and more area under the PDF curve, and it is approaching the total probability on the far right, which has got to be 1. The graph of the CDF for a discrete distribution is it's actually a series of horizontal line segments increasing in height from left to right, starting at 0 and ending at 1. So it looks kind of like, we'll have a piece that's 0 up to the first real bar, and then it'll be at the height of the bar. It'll go along till we get to wherever the second bar is. However tall the second bar was, that's how much, say if it was 2 of these blocks tall, it would go up that much more, and it goes along till the next bar and jumps up a certain amount, and eventually somewhere up here it ends up at 1 and starts at 0 for the y value. And so that's the CDF, and the PDF basically is a bar here, and the bar here is 2 tall, and the bar here was only 1 tall, and the bar here was only 1 tall. And when you add all these units together, you get a total of 1 actual unit. So that's what a CDF looks like in a discrete case. In a continuous case, it's going to start at 0 and work its way up to 1 here. But it's going to be connected and increasing, or possibly level in some places. So let's see. I believe this answer is correct there. Because you're careful about discrete and continuous. Graph of the CDF for continuous distribution, increasing connected curve, starting at a height of 0, increasing to a height of 1. It is increasing. It could be level in some places, so it's technically non-decreasing, but it's basically increasing. Although it may have sections that are horizontal. For a continuous distribution, the probability as x is less than a is seen as on a CDF graph, it's the y value for the CDF above that particular x value, so that would be b. For a continuous distribution, it is, okay, now notice this changed CDF to PDF. So on the PDF, it is an area between the PDF graph from forever left up to that x value, so that would be b. So what we're saying here is when we have a graph here, and let's say down here we have maybe the graph of the CDF. This is the x-axis, and we want to pick a particular x value c here. The probability that x is less than c is, under the PDF, it's this cumulative area, and under the CDF, it's this y value. Say the y-axis is here, so that y value is the is CDF of c. And so either way, this y value, this area, that output value, the y coordinate there, all that is the probability that x is less than c. Okay, next. Okay, keep going here. In both discrete and continuous probability distributions, the output of the probability density function is non-negative. It's never negative. I should say positive there. It's either positive. It could be negative. It couldn't be 0. It might not be always positive, but it's definitely never negative. So non-negative is correct. The graph of the PDF of the discrete distribution is distinct vertical bars, and the height of each bar is the probability. The graph of a PDF of a continuous distribution is a curve. The height of the PDF graph for a discrete distribution is the probability associated with that particular input. That is true. The area of that bar is proportional to the probability. So the probability is the height divided by the, or is the area divided by its width, which of course is the same as the height. The height of the PDF graph for continuous distribution is the probability associated with that particular input. That is false, because when it's continuous, the height of the curve on the PDF graph really is not. It's not the probability. The probabilities are areas. For discrete distribution, areas between the top of the graph of the PDF and the x-axis are probabilities. That's really not necessarily true. That if the bars all have width 1, then that might be true, but otherwise it could be false. For discrete distribution, areas between the top of the graph of the PDF and the x-axis are proportional to probabilities. That is true. You need to divide out by the width, assuming they all have the same width. For continuous distribution, areas between the top of the graph of the PDF and the x-axis are probabilities. That is true for a continuous case. Alright, let X be the amount of coffee distributed by a machine in fluid ounces. Assume that X is distributed uniformly from 7.5 to 9.1. We'll go down and see what we have here. Give all final answers rounded to 2 decimal places. Okay, so it's they said it's uniform 7.5 to 9.1. So scratch paper here. Some 7.5 to 9.1, wherever that is here. So from the right of 9.1 it's 0, to the left of 7.5 is 0, and it's some height in between here, some right scale. It should be a horizontal line right across there. So basically we have a little rectangle right here of area 1. The base of that rectangle, overall base, is 9.1 minus 7.5. Let me just make sure I read those numbers right. 7.5 to 9.1. Right. So, get a little bit lazy here. 9.1 minus 7.5. That's 1.6. Okay, so that's a width of 1.6 units. And the height, well, I know the base times the height is 1, is the area, which is 1. But the area is also base of 1.6 times height of 8, so h is 1 over 1.6, or multiply top and bottom by 10. That's 10/16, or reduces to 5/8. So that's 5/8. Okay. And so actually the graph of the height is the PDF. So PDF of X is just 5/8 for X's between 7.5 and 9.1, and just 0 otherwise. So we can ignore everything outside of this interval. So when I go here, if I want to graph this, I only want to graph between 7.5 and 9.1. Okay, and I'm going to go to this here, and we're going to turn off some stuff here, and I've got a PDF, so I'm going to put this down in Y7 in case I want to do anything else with it, like make a CDF. I don't know if I need that or not yet, but the formula is very easy. It's just 5/8. And so if I graph this, I should see a horizontal line. And of course, if I find the area, let's just calculate to be sure. Calculate that area, and I'll shade it, between 7.5 and 9.1. Then that turns out to be, should be 1. Okay, that's good. And I'm going to clear that drawing off. Okay. Alright, so what's the probability that has less than 8.4 ounces? Well, that's between 7.5 and 8.4. I can do it this way and even shade it by doing from 7.5 to 8.4. That'll shade it and compute it. And it says 2 decimal places, so 0.56. Okay, that looks good. 8.4 and 9, in between there, we can just go from 8.4 to 9. Now we have to be careful, because if it goes outside this interval, we can cut it off. Like, for example, less than 8.4 should be from negative infinity up to 8.4, but from negative infinity up to 7.5, there's nothing there. So we just had to go from 7.5 to 8.4. 8.4 to 9 is all inside the interval. I can go ahead and clear this and just do a probability by calculating this. Of course, this is just a rectangle, so we could easily do this by hand, even without a calculator. But this will also shade it and compute it for us. And that rounds off to 0.38. Now the next part, I'm going to go to the home screen, and I want to do Math 9, which is gives us our area calculator there, or our continuous summer, if you want to think of it that way. It's also called the definite interval. And we want to do it for all possible x's, so in this case the lower bound would be 7.5, the upper would be 9.1, but we're looking for the expected value of x, which is always x times the PDF. PDF, I believe I have in y7, so we get that from variables, y variables, function 7, and the last part's always just an x from the dx. Because, well, you could use other variables, but we're always going to use an x. And this should give us the mean amount here of 8.3. Okay. We also had looked at some shortcut formulas for finding the mean of a uniform distribution. If you remember that formula, you can use it as well, but we're going to go ahead with this. Okay, next. Researchers at a university have designed, built, and tested a switched capacitor circuit for generating random signals. The circuit's trajectory was shown to be uniformly distributed on the interval from 0 to 1. Well, notice 0 to 1 is a length of 1, so that means it must have a height of 1, too, to have an area of 1. So it's basically a little square we're looking at. So if I come down here, I can do the same thing that I did before, but I'm going to replace this 5/8 with just 1. And I'm going to replace my interval, we call it, with 0 to 1 for x. I'm going to do that one. Maybe we'll mark it off in tenths. Okay, and so this area here that we're looking at is 1. It's 1 wide and 1 tall. Okay. Mean and variance. Well, one way we can find the mean, again, is the expected value of x. So the mean is the expected value of x, and that is we take the x times the probability function of x and integrate over all x's. So in ours, that's going from 0 to 1, x times 1 dx. Okay, and so we can do that from the home screen. Math 9, go from 0 to 1, x, and then dx, and we get 1/2, or 0.5. So the mean is 0.5. Variance, remember again, is the expected value of x minus mu square. So this is a measure of the spread. That was the half was a measure of the center. And of course, it's the center. We didn't have to do all that for the mean. The mean's pretty easy. It's just the average of the two ends, right? Because if it's going from 0 to 1, halfway in between will be a half. And because of the symmetry of this, well, it should be a square actually because it's 1 tall. The symmetry involved, that's going to be 1/2. So we know this mu is 1/2, or 0.5. And we do x minus that square times the PDF, which is 1. and add that up for all x's, which in this case is 0 to 1. So what we want to do is we want to take, I can go second enter. Okay, so that 0 and the 1, the dx are already set up. I just have to work on this part in here, parentheses, x minus 0.5, close parentheses, square. Okay, that looks right, times 1, because 1 is the probability density, and this gives us 0.083 repeating. By the way, we can change that to a fraction, and we get 1/12. Okay, we also may remember the shortcut formula. The variance is b minus a squared over 12. Well, the b minus a is 1, so that's 1 minus 0 squared over 12 is 1/12. But we need a decimal. 0.0833. How many decimal places do we need here? It doesn't say. Oh, there it does. 3 decimal places. 0.083. Okay, good. What about the probability between 2 and 7? Well, we can do it from the home screen. We can go Math 9, and we can go from 2.2, that should say, to 0.7, which is in the interval 0 to 1. And we're integrating the PDF formula, which I put in y7, but it's going to be easier for me just to type in the formula here now, because this one, the formula is just 1. And then, of course, this is always dx. And that turns out to be a half. We can also see that on the home screen, on the graphing screen, rather, by going to here and going to number 7 for our area calculator and going between 0.2 and 0.7, and it'll graph it and give us half the area shaded. Do you expect to observe a trajectory that exceeds 0.994? Okay, well, let's see. Well, what would that probability be of that little? It's going to be a little bitty sliver here. We can actually compute that. Just pull up that second entry, and we want to go bigger than, let's see, we want this to be 1, because we want to go all the way up to 1, but we want to go down as far as 0.994. Well, that's 0.006. Okay, so that's going to be pretty rare. So we're going to say no, we would not expect to observe a trajectory that big, because the probability is very small, very unlikely, and it's actually equal to only 0.006. Moving along. Psychology students at a university completed the dental anxiety scale questionnaire. Scores on the scale range from 0, no anxiety, to 20, extreme anxiety. The mean score was 12, and the standard deviation was 3.5. Assume the distribution of all scores is normal with that mean and standard deviation. Okay, so let's graph that. Let's turn off what I've got down here, y7. PDFs I like to put here, so I'll go ahead and put it in y7, but I'm not going to use y6 because I've got a better version. So I'm going to go to distribution, and I'm going to graph it. I need the normal PDF, and I just want to do it at x, and I want to go from forever left, negative infinity, up to x. Okay, so now how far out do I need to go? Well, a let's quit this for just a second. Generally speaking, if you can go out 10 standard deviations, there's practically nothing beyond there. Theoretically, there's something there for probability, but in practical purposes, it's so small that it can be ignored. So if we'll just do mu 12 minus 10 times the standard deviation of 3.5, so negative 23 or anything a little bit to the left of that would be good for a negative infinity. And if we need a positive infinity, we can go 10 standard deviations above the mean. And if this is some nasty number, just round it off a little bit, a little to a nicer number. So, if you'd rather use 50 instead of 47, that's okay. So we need a negative infinity, so we're going to go negative 23. So let me go on down here. I can put this in y1 or anything, it doesn't matter. But the syntax is lower bound, normal PDF, lower bound, no, I'm sorry, I'm thinking of CDF. PDF, there is just the x value. Then you give it the mean and the standard deviation. It's a little bit simpler. So mean and standard deviation. So mean is 12, and standard deviation is 3.5. And okay, where do we need to go? Let me show you something we can do here. We could take the 12 and store it as the mean, store it as m, and the standard deviation 3.5 stored as s. And if we'll graph, say 4 standard deviations below the mean to 4 above, we're going to be in good shape. So for this, we want to do essentially just do the mean minus 4 s's, 4 standard deviation, 4 sigmas, and we could do the mean plus 4 sigmas here. So negative 2 to 26, that should be a pretty good window. That'll put the mean 12 right in the middle of it. And we may be going up too high here, but we may want that later for a cumulative distribution. So I'm going to start by doing this, and hopefully I'll see a little bell-shaped curve. It's kind of short. For the moment, we might want to zoom in a bit. So I may set the top a little lower, maybe 0.4 or something. If I want to do that, maybe go to 0.02. Let's see. So this should be our whole normal bell-shaped curve. Okay, what's the z-value? Well, remember that the z-value is a standard score. It's how many standard deviations you are above or below the mean. So it's our x value minus mu, and then divide by sigma. So in our case, mu was 12 and sigma was, I believe, 3.5. And we want to see 18 on the scale. So this is 18. So that's, well, I can do part of that in my head. That's 6 divided by 3.5. .714285. Actually repeating, that's a repeating decimal. Okay, so alright, let's get that in the calculator. Round to the nearest hundredth, so 1.71. Now, if you're going to do this by using tables, you really need that z-value to look this up, look the probabilities up on a standard normal distribution. But we really don't need to do that on the calculator. So that's not going to be as important for us. We want to find the probability, but x is between 11 and 16. Now we've got several different ways we can do this. I can still do it the way we've been doing some of these earlier, but I've also got some shortcuts. And if I want to find probabilities on the normal, the easiest way to do it is number 2, the normal CDF. Now notice that was second variables, which gave us distribution, DISTR, and it was number 2. Normal CDF. Okay, now this is the one where we have to start at the left, then the right, so 11, then 16, and then we give it the mean, which was 12, and then the standard deviation is 3.5. If you leave off the mean and standard deviation, assumes it's standard normal, that is a mean of 0, and standard deviation of 1. And so this is going to give us the area that we need, the probability we need. And on the CDF curve, this would be a difference in two y values. So it's actually the CDF evaluated at 16 minus the CDF evaluated at 11, which is exactly what we want. We can also shade this pretty easily by going to distribution and going to draw, and you can do shade normal, and you give it, again, the exact same thing on the inputs. You give it the left side, the right side, the mean, and then the standard deviation. And hit, I didn't mean hit graph, what I should have hit is enter. And so just hit enter, and it will graph it. Even if you didn't have it graphed already, it'll graph it and shade it, tell you that's between 11 and 16. Same value. So this is essentially doing exactly what we were doing before with doing this numerical integral thing, but it's just doing it where you don't have to use that particular command, so it's built in. Okay, find the probability that somebody scores above 17. Okay, so again, what we're doing here is we're looking at a normal curve, and we want to find from 17 up to the right. Okay, so here's where we're going to have to use an approximation of infinity. Okay, so notice, remember, I've got in M, I've got the mean, and in S, I've got the standard deviation. So I may refer back to that later. So we're going to do a probability of greater than 17. We want to find probabilities for normals. We want to use the normal CDF, number 2 there, so distribution, number 2. And we want to go left in, which is 17, right in. Now the right in should be infinity, but we've already said that what we can do is put in the mean plus, so let's say about 10 standard deviations, and that we can just type it in like that, since I've got the M and S stored. And then we need to give it the mean. Well, we'll just go ahead and put in M and S because I've got the right thing stored. And there we go, 0.0766. 0766. Okay. Okay. The physical fitness of a patient is often measured by the patient's maximum oxygen uptake, recorded in milliliters per kilogram. The mean maximum oxygen intake for the cardiac patients who regularly participate in sports or exercise programs is found to be 25.6 with a standard deviation of 6.3. Let me just go ahead and save those. 25.6 is, I'm just going to store that as my mean, M, and the 6.30, I'm going to store that as the S. So I can just refer to the mean as M and standard deviation as S. Okay, pay attention whether they tell you the standard deviation or the variance. You want the standard deviation here. Okay, and it does says that it's normal or close enough that we can use a normal to model this situation. What's the probability that a cardiac patient who regularly participates in sports, and that's who this particular thing is for those who are in sports or exercise, and it is a distribution of their maximum oxygen intake. So this is the appropriate thing for this. And we want at least 20. So at least 20 means X is greater than or equal to 20. So it's 20 and up. So again, to find the normal probabilities, we go to here to compute the probabilities. We're going to go to number 2, and we want to go from 20 up. How far up? Well, infinity, but remember we said we can just do mean plus about 10 standard deviations, however many that is. and we have to give it the mean and the standard deviation. And notice I'm making good use of storing variables here, but of course you could type those numbers in instead. 4 decimal places, that's 0.8130 when that rounds off. Next question. What's the probability that the X, the maximum intake of oxygen, is at 10.5 or lower, less than 10.5? So this is going to be just like the last one, but the lower side is going to be minus infinity. So let's see. So instead of minus infinity, we can use about 10 standard deviations below the mean. So it's mean minus 10 standard deviations. And we're going to go up to 10.5, and with that given mean and standard deviation. Make sure this is a normal CDF, not PDF. It's real easy to get off on that. So be sure you have the right one there. And that is not very likely, 0.0083. Less than 1%. Consider a cardiac patient with a maximum oxygen uptake of 10.5. Is it likely that this person participates in the sports or exercise program? No, because they're not taking in the amount of oxygen that would normally be expected. There's only a, if they were in a sports program and they got this level or lower, there's less than 1% chance that would happen. So it's much more likely that this person just is not an exerciser. How many questions do we have here? Just one more. Okay. The mass of a bearing manufactured in a factory is distributed normally with a mean of 17.78 grams and a standard deviation of 0.98 grams. Product specifications call for the bearing to have a mean mass of 17.83 grams within 0.1 gram. Okay, we'll get back to the specifications in a minute. Let's go back here again. This is a normal distribution, and we know the mean and standard deviation. So once again, I'm going to just store this in 17.78. I'm going to store that as my mean, alpha m, and I'm going to take these 0.98, store that as my standard deviation. Okay, so those are stored in, so now I can just use m for mean and s for standard deviation. I'm actually going to use L for lower spec and U for upper spec here too. So the target spec is 17.83, but we could be as low as 0.1 below that. So that's 17.73. I'm going to store that as L. Okay, for the lower limit of a good bearing. And a bad bearing, a good bearing could go as much as 17.83 plus 0.1. This would be the upper limit of how good a good bearing could be. So I want to store that as U for upper. I do this storing because I like to not have to type in as much stuff later. What proportion in decimal form, to 4 places, of the individual bearings are within specification? So we want the probability that a particular bearing is between the lower L and the upper, between 17.73 and 17.93. Well, this is a normal distribution, so I go to second distribution, and we're computing a proportion, which is a probability. Okay, so we go to number 2, and we want to go from lower L to upper U. Those are our lower and upper product specifications. Not necessarily the lower and upper bound of what we actually produce, because we could be producing some bad items here. And we need to give it the mean next, and then the standard deviation here. So by making all these letters stored, I can just kind of put what they mean here. Of course, I can just type all these numbers in here. 17.73 instead of the L, instead of the U, 17.93, instead of M, 17.78 instead of S type 0.98. You will not have tables available on the test, but you should have your calculator and are expected to use it. Tables are not accurate if they go beyond the number of digits that they have, or you have to interpolate for values in between. So oftentimes that you can use a 4-digit table and yet only get answers that are good to maybe 2 digits. So we can use the calculator and get answers that are as accurate as our data will allow, probably, because we got 10 digits or something like that. Okay, continuing on, pistons that are too large can be reworked, but pistons that are too small have to be scrapped and recycled. Perhaps the large ones can be filed down or something. But if they're too small, we just got to melt them down and start over. Okay, what proportion of bearings are scrapped? So, if X is the mass, we're finding the probability that X is less than the lower limit. Okay, so we can do, let me just pull up our previous answer. And we're going less than the lower limit. So the top bound right here where I've got the U should be the lower limit, L, lower specification limit. And where I've got an L, it should be, well, it really should be minus infinity. But if you remember, what did I tell you to put in for instead of minus infinity? You can put in the mu minus, let's say around 10 standard deviations. Let's see if I've got everything typed in. Whoops. I hit pi instead of alpha. I must hit second instead of alpha. Got to get on the right one too. It should be mu, which is m. There we go. And be sure we are on a normal CDF cumulative distribution, which is going to be the one that actually gives you outputs that are probabilities. So it's the mean minus 10 standard deviations up to the lower, which is our approximation of negative infinity, up to the lower spec limit, and then with that mean and standard deviation that we have, and that is 4797. 0.4797. We got a certain percentage of the time the mass of the bearings is smaller than what value. Now this is an inverse normal, and normally before, when we were doing these types of problems, we would have to draw the inverse normal, which looks something like this. Starts at 0, works its way up to 1, and in this case the inflection point happens here at the mean. And somewhere over here there's the axis, okay, 0. And what we want to do is, of course this is the x-axis here, and this is y equals 1. And what we'd have to do is we'd have to put in that 0.99 whatever up here. It's a little higher than that actually. And we just calculate that x value by calculating an intersection. Well, this is built in basically with an inverse normal. So we've got a really nice shortcut for this one since it's a normal. Normal is so important. An inverse normal is built in. You just put in the probability, 99, what was it? In the decimal form, 0.997739. And then we give it the mean and the standard deviation. I've got those scored, remember, as alpha and m and alpha s. So m for mean and s for standard deviation. If you leave off the m and s, it'll give you the z-score for this number. That is on a z distribution or standard normal distribution. But this gives us remember the input here is the cumulative probability, and the output is the x value we're looking for, which in this case is a mass of a bearing. Okay, a random sample of 17 bearings is taken. The masses are measured and then averaged. Since the individual piston masses are normally distributed, the distribution of these sample means are normally distributed with a smaller, with the same mean, but smaller standard deviation. So distributed normally with the same mean. Good. What's the standard deviation? Well, standard deviation is the original standard deviation, which was whatever S was, divided by the square root of the sample size. And the sample size here was it 7? Yes, 7. Okay, so what this is saying is that the mean of the mean of the means is the mean of the individuals. That was the answer to the first question, or the previous question. And the standard deviation of the means is the standard deviation of the individuals divided by the square root of the sample size. So here we go. 0.3704. 4 decimal places for everything. What proportion in decimal forms of the average values of the x bars are less than 18.299? So remember, the x bars are distributed normally, same mean, but a smaller standard deviation. So this new standard deviation, let me store that as something else. I'm already using S for standard deviation. Maybe I'll use R. So R is the new sample standard deviation. Okay, but it's still a normal distribution, so I can use normal CDF to compute probabilities. We want less than this. Well, we can use mu minus, actually 10R will do it, which is even, but certainly 10S will also do it. Anything for negative infinity. And then we want to go up to, well, 18.299. And we want to do it with the mean of M. But be careful, we want to use not a mean of S, but a mean of this S divided by square root of 7. So I can type in S divided by square root of 7, type in the 0.37 whatever, but since I've stored it as R, I can also just type in R. And that's going to be pretty high. 0.9194. What proportion in a decimal form of average values are within the product specification? So again, we're doing a normal distribution. Okay, we want the mean M and standard deviation R for this particular distribution of sample means, but we are wanting to go from the lower specification limit to the upper one, whatever that was. I've got them stored, so let's get to that. Let's see, get rid of some stuff here. Okay, I think that's it. From the lower to upper specification limits, centered at M for the mean, and standard deviation is this R, which was the original S divided by square root of 7, and we get that 0.2109. Alright, I think I've got everything. So make sure I didn't miss anything here. I'm not going to go back and check everything, but notice I do have some time left, so if I were actually doing this for a grade, I would probably go back and check my work a bit. I'm going to at least check and make sure I answered everything. So notice those last set of problems were about sampling distributions, our very last section. Alright, let me go ahead and submit. And I got 100%, so very good. So that's a good, complete, and accurate solution set for the practice test. Hopefully you can use that to study. The exact real test will be somewhat similar to this, but could be a little bit different. It may have a few more, a few less questions, more or fewer questions, I should say. It should have maybe some of the same questions, which are algorithmically generated with new numbers, but maybe some different ones. So this will be good help for you to study. Good luck studying, and good luck on the exam.